a quick review of what an electron configuration is, right? What is electron configuration? Nothing? No ideas? What? Just based on the word configuration, what does it probably mean?
The electrons are configured.
Yeah, where they're configured, how the electrons are configured, where they're located, right? Kind of. So we're not going to go over the Bohr model, which is like where you have like first level, second level, and you have this ladder worth of electrons. This is more geared toward the quantum model. And the quantum model deals with electrons being located in what's called orbitals, right? Orbitals are electron pockets. That's what contains the electrons. And then within a energy level, there are different types of orbitals. Do you remember the orbital types?
Is it the thing, and then you go over, so it's like, I can't explain it well, but it's like 1, 2...
When we deal with electron configurations, we are going to start identifying where all of the electrons within a certain element are located, right? That's what we're going to tell them. How many electrons are in the s orbitals, the p orbitals, the d orbitals, and the f. So first things first, we need to identify on your periodic table that you know there's a relationship between the s orbitals and the periodic table. A relationship between the p orbitals and the periodic table. And so I want to go over those relationships first, and then we'll kind of dive in a little bit more. So electron configurations, let's go back just a tiny step here. Actually, maybe I'll go forward. Let's go into the orbitals and their shapes, okay? Actually, I want to go back here. Let's talk about the orbitals themselves, okay? There are 4 different types of electron orbitals. These are not in your notes. I'm just kind of ad-libbing this part. So you can put it off to the side, put it in between, whatever. Okay, there are 4 types of electron orbitals. S, P, D, and F, right? Those are all the main types of electron orbitals. Is those ringing some bells a little bit from last year? Or 2 years ago, maybe? Okay, there's S, P, D, and F orbitals. A single orbital can hold how many electrons? Do you remember? It can hold, a single orbital can hold 2 electrons. And then there's a bunch of different types of different orbitals that hold more than that. Okay? Now, the patterns for the orbitals and their maximums are mimicked on the periodic table. Sometimes in Chem 1, we put a really heavy relationship between, well, it's on the periodic table, so this is what it is. But realistically, it's just the pattern that's mimicked. It's not, we don't need to depend on the periodic table quite as much, but we do. It helps us see this pattern. So let's go over our orbital shapes a little bit. An s orbital, there's only one type of an s orbital, so it can hold a maximum of 2 electrons. And it's like a sphere, okay? It's just like a circle that envelops the nucleus, and those first 2 electrons that go into any element get added to the s orbital. Okay, so anytime a molecule is built, the first 2 electrons that get put into the s orbital. Okay, the p orbitals are next. There are 3 versions of the p orbitals. 3 versions of the p orbitals. We're going to see that here in a little bit. That means they can hold a maximum of 6 electrons. Okay, and they kind of look like this, kind of like a little dumbbell shape. And there's 3 of them. So it ends up looking like this kind of flower around the nucleus. Okay, and you have the shapes in your notes, in your slides, in a couple here, so you'll be able to see them a little bit more clearly. Okay, but the p orbitals can hold a maximum of 6. The d orbitals, there are 5 different versions of the d orbitals. So how many electrons total can the d orbitals hold? They can hold a total of 10 electrons. And they have a much more intense shapes. We're going to see those here in a second. Last one is the f orbitals. And they can hold, there's 7 versions. So how many can they hold? They can hold a total of 14 electrons.
Isn't that, so like S is...
Understand the reason behind the patterns that get mimicked on the periodic table. So this is the most important part of it, knowing that the s orbital can hold 2 electrons, the p orbitals can hold 6, the d orbitals can hold 10 total, and the f can hold 14. So let's look at how that's mimicked on the periodic table. If you look at your periodic table, you'll see these colors have the groupings done. So the the s orbitals can hold a maximum of 2 electrons. So let's say if we look at, let's put helium over here for a second, okay? If we put helium over here, the first 2 electrons that get put into helium have to go into what type of orbital? S, right? Because we said S holds the first 2 electrons in every element. Okay, and so this is called right here the S block. Okay, the first 2 elements, the first 2 groups are called the S block. Okay, the S block of elements. And the reason for that is because any element that's found in the S block has its outermost electron in an S orbital. That's what it means. Okay, do you want me to say that again? If it's found in the S block, that means the last electron in that element has to be found in an S orbital. Okay, and sometimes I think that parallel is lost when we first do this electron configuration. So the reason it's called the S block and they're called S block elements is because their last electron is found in an S orbital. Okay? Then we move over across the periodic table. After hydrogen and helium, we move down an energy level. Okay, so on the periodic table, when we move downward, we get a whole new shell of electrons, right? We add a second level. So let's look at boron, for example. How many electrons does a neutral boron have? How many electrons would a neutral boron have? 5, right? Its atomic number is 5, so it would have 5 electrons.
Oh, and they go up, so it's 5, 6, 7.
Right. So the first 2 electrons that go into boron have to be in an S orbital. Right? Would you agree? The second 2 electrons that go into a boron have to also be in an S orbital, but now they're in the second energy level S orbital. Okay, so if I've got boron's nucleus, we've got 2 electrons found in the first S orbital, 2 electrons found in the second S orbital. Okay, are we there so far? No. Okay. Here's the deal. Anytime we go down on the periodic table, that means we add a whole nother level to our atom. We add a whole nother shell. We restart with an S orbital when we move down on the periodic table. Okay? So since boron is in the second row, right, of the periodic table, that means it's got 2 levels of electrons. Okay, the first ones go in the 1s orbital, then the second ones come down, and they have to also enter into an s orbital, right? It's kind of like, think about this. To get past here, to get to boron, we had to fill the s orbital. Then we come over, and boron's outermost electron is found in what's called the p orbitals, or this little pink section of the periodic table is called the p block. Okay, so let's rewrite that. Let me get rid of all this extra junk. This is s. These are p block orbitals, okay, or p block elements. That means any element found in this block of elements has its outermost electron in a p orbital. These ones are found in these are called d block, and then this down here are called the f block elements. So whatever block it's in, that tells us that its outermost electron is found in that block or in that type of orbital. Okay? We go exactly in this order. So we'll fill up the 1s block, then we come down and fill up the 2s block. Then we fill up 2p. Then we come fill up 3s, then 3p. Okay, so when we fill electrons and we start to look at building an atom and filling electrons in that way, they need to go exactly in the order of the periodic table. Okay, does that kind of make sense? There's a couple shifts that are made, and I'm going to show you here on this next one. It has them laid out. You see how this first one of the D block is labeled 3D, not 4D? Even though this is 1, 2, 3, 4. Do you see why that is? Okay. Now, this is something you'll just have to kind of remember, because these elements, the d orbital really opens up in the third energy level. But we can't shift it on the periodic table because it messes everything else up, right? So you just have to remember that the d orbitals or the d blocks are just shifted one set on the periodic table. But you still order them in the same way. So as I'm filling electrons, if I need this many electrons, 22, this is element number 22. If I needed 22 electrons, my electron configuration would still 1s2, we fill those, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2. Right? It still fills in the exact same order. Okay? Does that kind of make sense? In Chem 1, I've given you like this little pathway thing to follow. I don't think we really need that. I think we'll be able to just follow along the periodic table and fill our electrons in the right order in the just based on those blocks. Okay? Second thing is the F blocks usually would fit right here. Same thing here. They become available at the 4th energy level and the 5th energy level, not 6 and 7. So those are ones you'll just have to kind of remember, that the d orbitals are shifted 1 and the f orbitals are shifted 2 from where they really kind of fit in. Okay?
So you don't start doing, when do you bring in the F?
The f orbitals fit right here. You know, this one would come fit in this line right here. Anytime you would, if let's say I needed this element right here, okay? If I needed this element, I would go 6s2, then I'd come 1, 2, 3, 4, 5, 4f5. You know what I'm saying? 4f would come right after I fill 6s in between those guys. Does that make sense?
Oh.
Okay? So you have to see where it's supposed to fit in on the periodic table, and then we can check that. Okay? Is at least this part of it coming back? 1s2, 2s2, that kind of stuff? Is that coming back a little bit? Okay, I figured that it would. There's a way we can always check our electron configurations. Do you remember how we can check that? Let's go ahead and try one here, and we'll see what we think. Give me the electron configuration for, I don't know, let's do aluminum. Let's do electron configuration for aluminum. Tell me what, first of all, when I want the electron configuration, I'm always asking for right now, for like the neutral state, ground state, no charge, no nothing, aluminum. And so what block is that in?
P.
It's in the P, and is it in 1, there's no 1P. Is it in 2P or 3P? 3, right? Even though you still have to count hydrogen and helium's group or row. So 1, 2, 3. So in order to get to aluminum, I'm looking for this guy right here, which means I need to fill 1s2, 2s2, 2p6, 3s2, and then 3p what? 3p1.
Wait, okay,
Where's
so
the-
1s and then 2s.
1s comes here, then we go 2s, then we work our way across. We have to fill up the 2p, then we fill up the 3s, and then we come over here to
What are the-
3p.
Exponents.
These up here tell us how many electrons are in that particular orbital. So we said the s orbitals can hold 2 electrons. That's where the 2 comes from. We said the p orbitals can hold 6. The way we can remember that is we come look at the p block. 1, 2, 3, 4, 5, 6 groups within that p block. So that helps us kind of remember how many they can hold. How many did we say the d orbitals could hold? Look back at your notes there. 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? It tells us that right on the periodic table. So when I said those patterns are mimicked, that's true, right? The periodic table wasn't built to match electron configurations, it just works out that way.
And then those only fill, these fill 14, F does.
Right. So if you count F block, they had 14 there. So the way you can check your answer with electron configurations always is to add up, because these are your numbers of electrons. Right, so 2 plus 2 is 4, plus 6 is 12, plus 6 is 10, plus 2 is 12. That's 13 total electrons. Is that how many aluminum was supposed to have?
Mm-hmm.
Yeah. Right, so you're able to check yourself based on your electron configuration. Okay? All right, what questions do we have regarding building the electron configurations? I feel like that's probably something we feel okay about, just in terms of we've already learned it once. I wanted to brush up on a couple things. But do we feel okay about that so far? Okay, great. Let's take a little bit closer look then at the shapes of the orbitals. I don't have S up here because S is just a sphere, right? S is a sphere. It sits right directly around the nucleus. It envelops it. There's only one version of the S orbital because no matter how you move it around the nucleus, it's still a sphere. You know what I'm saying? Can you envision that? You put a sphere around the nucleus. It doesn't matter which way you turn it, shape it, what axis it's on, it's still a sphere. But the p orbitals are a little bit different. We said there's 3 versions of the p orbitals. One that's on the x-axis, one that's on the y-axis, right? Here's x, here's Y, and here's Z, right? Oh, sorry, I accidentally did the wrong one there. X, Y, and Z axes, and those are three-dimensional space, right? They're taking up three-dimensional space around the nucleus. And so each of these orbitals can hold 2 electrons, right? So here could be 1, and there could be 1, 2, 4, 5, 6, right? There's where our 6 electrons for the p orbitals are found. 1 in each of those little pockets. Okay, and then the way they orient themselves around the nucleus, they give themselves enough space so that the natural repellent that happens with electrons, they still have enough space to kind of be okay or happy. Okay, so there's the versions of the p orbitals there. And then this little cloud picture of what it might look like. It says, generated by a program, Robert Alvendorfer, I don't know, he did. Okay, so he did some electron, like spotting, basically. Right, he was able to track the location of this electron within that orbital, and there's how much movement happens in an orbital of a single electron, right? Electrons are constantly in motion, but they've got this boundary, right? And so there's kind of the boundaries that happen within that orbital. All right, boundary surfaces of all the 3D orbitals. There's all the versions of the 3D orbitals. You'll see 4 of them really look alike, and then the 5th one looks way different. Right, it's got this kind of cone, like donut thing going on in its 5th orbital. Not something I'm going to need you to remember in terms of the shapes of the orbitals that much. I do need you to know that there's different versions of them, and they do look different, and they're oriented differently around the nucleus, but that's all we're looking there. Okay, you'll notice too in the d orbitals, each of these orbitals kind of has 4 little pockets, so there might only be electrons in 2 of those at a time. Okay, all right, and then there's the f orbitals. A lot of crazy stuff. Imagine all of those together around the nucleus, right? Those are where electrons can be found. So it's really interesting how much bigger some of those pockets are than others. Okay, any questions about writing electron configurations? I want to go through noble gas or abbreviating configurations real quick. When we abbreviate electron configurations, we abbreviate with the noble gas. The noble gas ahead of it. Okay, so let's take a look at, let's do sulfur. Full electron configuration for sulfur would be 1s2, 2s2, 2p6, 3s2, 3p4 would be sulfur, right? But the way we abbreviate electron configurations is with the noble gas that comes ahead of sulfur. So what's the noble gas found in front of sulfur? Neon, right? So what I do when I abbreviate is I say sulfur's electron configuration is the same as neon plus whatever comes after that, right? You got to fill in what goes from neon to sulfur. So after neon, we come down here to, we need to fill what orbitals?
3s.
We need to fill 3s, and it holds 2. And then we go over to, 3p, and we count to sulfur 1, 2, 3, 4. Okay, so sulfur has 4 of its outermost electrons in p orbitals. Okay. If you look back at this screen here, this slide here, you'll see that the versions of the orbitals are called px, py, and pz. For right now, I'm not going to have you start differentiating what orbital version each one of them is in for now. I just want you to be aware that that might be something you're asked to do when you take college chem. You might have to identify sulfur is 3p2, px2, py1, pz1. You know what I'm saying? Sulfur is going to have to put 1 electron in each before it comes back to put the second one in. And that's a rule we're going to talk about here in a second. So you might have to eventually get to a point where you spell out the individual versions of the orbitals. That's not going to be something I'm going to ask you to do right now. Okay, but I want you to kind of be aware that it does go a little bit deeper based on the versions of those orbitals. Okay? Now we're going to talk about orbital notation. Do you remember what orbital notation is?
With the arrows?
Yes, good. Orbital notation is when we draw out our individual orbitals. Okay? Orbital notation is when we draw out. So I'm just going to write it out. Draw out orbitals and electrons. Okay, we draw out all of our individual orbitals. So let's start with one kind of an easy one here. Let's just do fluorine. Let's do fluorine. You don't have to write out the full electron configuration if you don't want, but let's start looking at what orbitals fluorine is going to need to have, right? Fluorine ends up in 2p, right? Agreed? But in order to get to 2p, we have to have a 1s orbital, we have to have a 2s orbital, and then we have to write out the 2p orbitals. Now, there's not just one version of a 2p orbital. How many versions are there? 3 versions of p orbitals. So we draw 3 lines and we label them as 2p, right? If we had a d orbital, how many lines would we need to have? D would be 5 and F would be 7, right? We have to draw out every version of that orbital. So like I was talking about earlier, this would be like px, py, and pz, right? Those are the different versions of the orbital around the nucleus. So now when I fill in for fluorine, the way you fill in your electrons actually makes a difference. We fill one orbital type before we move on to the next. 1, 2, 3, 4. And then in P, fluorine has how many electrons?
5.
It has 5. And so the order that you correctly fill electrons actually does make a difference. We don't just go 1, 2, 3, 4. We don't go in that order. We follow what's called Hund's rule, and we fill 1 electron in each orbital type before we come back to fill in a second one. So we're going to go 1, 2, 3, 4, then 5 right there. Okay, I know that the finished product doesn't look any different than if I would have just done 1, 2, 3, 4, 5. That looks the same, but we have to fill them in differently. Sophie, go ahead. Tell me what was your question.
What's the 7?
Yeah, I was just about to say that. I forgot to even talk about what that was. These little half arrows are indicative of electrons. That's the electron. So these are electrons. One of them is pointing upward, one of them is pointing downward. They're both still electrons, but they're indicative of the spinning state of that electron. So when 2 electrons sit in an orbital, one of them needs to be spinning in the positive direction, the other one needs to be spinning in the negative direction. They have to do that in order to be able to coexist within that orbital. So when I draw them, I'm going to encourage you to always draw the positive one first. When you fill, then draw the negative one. Then we move on to the next section, and then we fill across 1, 2, 3, 4, 5 electrons. Sorry, I did go through that a little bit fast. Okay, any other questions about what that diagram kind of represents? Okay, if we were looking at, let's say, let's look at just nitrogen. Thank you. Let's look at nitrogen. Okay, it's very similar to fluorine. We're going to draw our 1s orbitals. We do need to have a label. We do need to have a label under that orbital. Okay, so 1s, then 2s, and then nitrogen is still in the 2p, but it's 2p what? 2p3. So I'm going to go 1, then 2, then 3.
If it's up, it's positive. And
Correct.
If it's down, it's negative.
Right. Yeah, good question. But this next slide, you'll see right on the next one, there's a rule called Hund's rule, and that's what we have to follow when we fill in our electrons. I'll just read it to you here while we're looking at this example.
Wait, when would it be negative?
When would it be negative? Tell me, what do you mean negative? Like, when would I put the negative electron in?
Well, like, why would it ever be a negative electron?
Well, okay, the charge on the electron is not positive.
Yeah.
The charge on the electron is not positive.
Yes.
It's just the way it's spinning. We call it positive, negative. One of them spinning one direction, one of them spinning the other direction.
So
it doesn't change its charge.
Negative. Okay.
I mean, it's still, the charge on the electron is still negative.
Yes.
But we couldn't have a positive electron, right? The charge of it is still negative. It's just talking about the way that it's spinning and its existence.
Okay.
Yeah, good question. Singly occupied orbitals must have the same spin state. So that means when I put in a single electron into our orbitals, they all have to be spinning the same direction. When I go to add my second one, that's when I put it in the negative direction, the opposite direction. Okay, it also says orbitals of equal energy, for example, the 2p's, they have to be occupied by a single electron before it's occupied by a second electron. And so what that means is that if I had like 3s after this, I wouldn't go 1, 2, 3, 4 before I come back, right? I have to fill the p orbitals 4, 5, 6 before I go on to 3s. Okay, think of it as like it's like a little climbing board. 1s orbitals have very low energy. 2s orbitals have a little bit more. 2p orbitals have a little bit more. 3s orbitals have a little bit more, right? So as we climb that energy ladder, we've got to fill the individual levels before we move on. Okay. So there's Hund's rule. We just talked about nitrogen's electron configuration. So there's I don't know if I had you fill in anything for Hund's rule or not, if I left that. Okay. Our orbitals of equal energy are occupied by one electron before any orbital is occupied by a second. So what that means is that all of the 2p orbitals, 1, 2, 3, all of those have the same amount of energy. But they don't have the same amount of energy as the 3s orbitals, right? Everything here has the same amount of energy, but not the same as the next level. Okay. Do we need to do another example on this one for phosphorus, or do we feel okay about that? Okay. All right, we're going to look just quickly here at something called excited state electrons. These are what happens when light is emitted, right? We talked about electrons being in an excited state, and when they come back to their ground state, that's when we see an emission of light. Okay, so excited state electrons are just electron configurations and they're not in their like base. They're not necessarily following all of the rules there. So this is an example of a carbon atom in an excited state. It would normally be a 2p type of electron configuration, right? Look at where carbon is. It would normally be 2p, but instead, one of those electrons has relocated from its s orbital into a p orbital, right? It's gained an energy level. And so that's what's considered an excited state electron. Not something that happens super, super often, but all that happened was our, where'd it go? Right here. This electron from 2s, what would have normally been 2s, has now jumped up to 2p. Okay, that's really all it means to be an excited state electron. If it asks you for that, you would just draw it with one electron moved, right? Unless it says that it has 2 excited state electrons or whatever it is. But you're just taking one of those last electrons and upping it at an energy level. Okay. All right, so this is just a little bit more about electron and excited state electrons. Did I give you anything to fill in on this one?
Yeah.
Okay. When an electron is in an excited state, it does have a higher energy. That's the whole point, is that it jumps up an energy level, right? It's excited. It's got more energy, right? Can you just picture it? I know. Okay, fine. I'm trying. You guys are like looking sleepy today. Okay. When that electron does eventually fall back, that's when we see an emission of light. And so now we can see a little bit maybe of connection between what we studied yesterday and what we're studying today, right? We've got a little connection there between those two things. So the wavelength of that emitted photon can be calculated using this equation. And we saw something similar to this yesterday, right? The energy of a photon. We saw an equation just rearranged like this where we solved for the energy of the photon, right? Do you remember that? It was just rearranged with wavelength and energy switched places, okay? And so delta E just represents the change in, right? When we solved yesterday, we asked what's the energy at that specific moment. The delta just gives us what's the change in it. It's really not making us solve it any other way. If we want to look at the energy level of a particular or a single type of atom, we're able to take in its energy level and its atomic number or its nuclear charge to find out the energy level in that particular moment. Okay, rather than the change in based on its wavelength or based on the excited state. So both of these, that equation and this new equation down here for energy, do you have those on there or do I want you to write those down?
We have them.
You already have them. Okay, great. Okay, here this N is our energy level. So when we have an element that's a 4s, energy level just comes from that right there. Right? The coefficient in front of that is considered its energy level. Okay? And then Z is its nuclear charge, and so all that really means is how many protons does it have? Okay, its nuclear charge is saying, what's the charge within the nucleus? Well, the only thing that contains a charge in the nucleus is protons, right? So if I'm looking for its nuclear charge, I just want to know how many protons are in the nucleus, okay? So, calculate the energy required to excite the electron, the hydrogen electron, from energy level 1 to 2. Calculate the wavelength of light must be absorbed by a hydrogen atom in its ground state to reach this excited state. So I want you to start writing out a couple things. We're going to be able to look at the energy level at level 1 and at level 2, and then we'll compare them, right? Or we'll do some math to get around those, okay? All right, so what are some things we know about a hydrogen atom? How many protons does it have? 1. It does have 1. Equation we just got for E. Right? E equals, read me that, negative 2 point what?
178 times 10 to the negative 18.
Okay.
Times z squared over n squared.
Okay. Times z squared over n squared. So for hydrogen, this becomes pretty simple, right? Because for hydrogen at energy level 1, that's what we'll look at first, right? What we're looking at is this hydrogen atom wants to go from a 1s orbital, it wants to jump up to be a 2s orbital, right? That's the goal. This hydrogen electron wants to go from 1s to 2s. So at energy level 1, that's what we're going to see first. Z, negative 2.178 times 10 to the negative 18th. Z is my proton number, right? So how many protons are in hydrogen? 1. What's the energy level? 1. Okay, so that's literally going to be 1 squared over 1 squared. So my energy level there is just negative 2.178 times 10 to the negative 18th, right? If I look at the same thing for energy level 2, the only thing that's going to change times 10 to the negative 18th is going to be my proton number stays the same, my energy level changes. So now let's go ahead and calculate it now based on like 1 over 4. So we're going to have to take a fourth of that number. .178 times 10 to the negative 18th divided by 4. 5.45 times 10 to the negative 19th. Agreed? Okay, that's a 19, not a 17. Okay, now I want to just find the delta of that change in energy. Okay, so I'm going to take final minus initial, which would be negative 5.45 times 10 to the negative 19, minus a negative again, right? 2.178 times 10 to the negative 18. That what we had there? A positive 1.63 times 10 to the negative 18th, and its energy should be measured in joules. This first part, right? Calculate the energy required. Then we want to calculate the wavelength of light that must be absorbed to reach that excited state. So now I'm going to find that other equation I gave you. And it said wavelength equals hc over delta E. Is that right? So delta E is that number you have in your calculator right now. I just keep that, right? In my calculator, I'm going to go alpha H times alpha C divided, put that in parentheses just to make sure. Divided by second answer. You know what I'm saying? This h is our Planck's constant. This is speed of light. That's the number we just calculated. So if I'm going to find the wavelength, I got 1.21 times 10 to the negative 7th meters.
And E is just that one thing right here.
This 1.63. Yep, we just solved that change in energy right there. And so delta E is going to be 1.63 times 10 to the negative 18th joules. And so this tells us the wavelength now of that, of the light that was absorbed in order for that hydrogen to reach that excited state. So let's go look at our spectrum. Go back to the beginning and see what kind of light is it. And is it visible light? And if it is, what color light? 1.21 times 10 to the negative 7. Let's see here. 1.21 times 10 to the negative 7. So we're right outside the visible light range, right? 1.21 times 10 to the negative 7th would put us, I don't know, right here somewhere. Oops, sorry. I think it would put us right here. Don't you think?
Yeah.
In UV light?
Wait, why wouldn't it be under radio waves?
Because it's to the negative 7th power.
Well, it's to the negative 7th power.
So we
But
go
it's
over
one.
the negative 7. Like
Well,
we
we're
go
looking over in this negative 7 to...
Uh,
So this is an in... Yeah, I think it's got to be here.
Yeah.
I think it's got to be on this side. Because 1 times 10 to the negative 7.
Yeah, that's not 4.
Well, yeah, I think we're not... We're not moving up to like... We're not moving closer to the negative 6th. We're closer to...
Yeah.
I think so.
So what color would it be?
There is no color. It's ultraviolet.
Right.
You can't see
Yeah,
it.
4 is smaller than 7, so that's what makes me think it's on this side of it. Yeah, okay. I don't know why I'm having number line problems right now, but apparently I am.